Hello and welcome back to Let's Code Physics. Last time in our Pendulum series, we were working with varying the lengths of the two rods in the double pendulum that we've been working with. And we saw pretty much the same graph every time we saw this type of result in our Poincare map. So just as a reminder, each dot on a Poincare map represents where the two speeds of the pendulum, the rotational speed of the top rod and the rotational speed of the bottom rod, both come to zero. And this is recording the angle of the bottom rod and the angle of the top rod whenever that special combination of values happens. And we were getting these two swooshes of dots here. We've got some scattered about here. I'm starting to think those are either noise in the data or garbage points or something like that, because they don't seem to appear with any kind of consistency. But the main feature are these two swooshes right here. And those didn't change all that much when we changed the length. Basically, this space where there were no points allowed just basically changed size. If we change the masses instead, the behavior changes a little bit more interestingly. Let's see what happens when we change the mass of the top pendulum. This again is the little ball at the end of the pendulum. This is one. So M1 is the one on top. M2 is the one on the bottom. If we make M1 bigger than M2, so let's say we make it 25%, we see that not only does the space grow, but the shape of these things starts to change pretty drastically. So we go from having them kind of curving around, almost looking like they're about to meet each other, to being pretty distant from each other. So they're not headed toward each other anymore. I even increased it up to 50% higher than M2. You notice we get much of the same. They're not curving as much anymore. That one is for later. Ignore what you just saw. Yeah, so you can imagine if we make this higher, these two are just going to continue to retreat. So that's kind of interesting. If we make M1 less than M2, so this is the top one is 90% of the bottom one, then this gap starts to close in and these arms start to reach toward each other a little more. Again, here is them being equal. Here's M1 being 90% of M2. We can keep going down. This one is 80% of M2, so you notice they're starting to become more parallel to each other. 0.75, so 75%. I'll let this one run for a while because this gap was starting to get closer in. If we make it 0.71, they're getting very, very close to each other. The two swoops are almost overlapping. Now, of course, a trained physicist or mathematician will look at this value and see that we're approaching a very special value, approaching square root of 2, 1 over square root of 2, square root of a half, which is a special number, right, that shows up in trigonometry a lot. It shows up as a normalization constant, 0.707 ... And so I went ahead and tried that out. I tried out M2 equal square root of 2 times mass 1. Gives you this interesting graph. So I let this one run for like a day and a half. So that's why there's all these extra points around here. But you notice there are two arms here basically meet right there in the middle. If you were to continue to let this go, you might see this fill in more. I had to move on to other projects, so I couldn't let it run for that long. But you get these two things meeting. So that's interesting. That tells you one way you could measure the square root of 2 would be to set up a double pendulum with equal arm lengths, and then have adjust the second mass until you get a Poincare map like that, and the ratio of the two masses must be 1 over square root of 2. Isn't that a perfectly reasonable way to find out the value of the square root of 2? If we go past that one, here's 0.70, so slightly off from 1 over root 2. Here we go to 0.65. Now you notice they've actually passed each other. So before, this left one was sweeping down on the left, sweeping down below. This one was sweeping down above. Now they've switched sides. So if you do it in fast motion, you can see them kind of evolving like that. And then if we keep going down to 0.6, this one's moving farther up, this one's moving farther down, but again, they're separating from each other by a greater distance. Same thing with 0.55 and 0.53. This one turned into a little bit of a mess. I'm not entirely sure why that is. The 0.50, you've got them separating a bit more, and you've got this gap widening even further. That was as low as I went just because the special behavior seemed to have stopped at that point. So if you want to see it in a nice animation, here we go. Here we are increasing. They come, they touch, and then they go away from each other. So the square root of 2 thing is really neat, or 1 over square root of 2. It's or square root of 2 over 2, depending on however you like to write your radicals. So the square root of a half ratio, or if you like, it's m1 equals square root of 2 times m2. So this is, oh shoot, I've been quoting those backwards. Okay, so reverse all the things I just said. This means that m2 is less than m1, not the way I said it earlier. Okay, I got them flipped around, my bad. So either way, one question would be whether this is a consistent effect. Like, is this always a special relationship here when you've got the square root of 2 ratio between them? So I tried another scenario where I made L2, the bottom rod, 10% longer than L1. Right, so because before I had the 2 rod lengths equal to each other, and here we've again got m2 equal to 1 over root 2 times m1. And you notice the 2 arms do not meet anymore. So this square root of a half being special must be unique to the 2 arm lengths being equal to each other. So if you have the 2 arm lengths not equal to each other, it's no longer square root of 2. So that tells me there might be some sort of Pythagorean relationship between the 2 arm lengths or something like that. But that's just speculation at this point. I need to play around with the values a little bit more to see. But I thought that was neat. That's kind of a neat way to see how this number that you see in math class really does show up in nature and really is important in the universe. It's not just a thing that mathematicians like. It is something that is fundamentally important to the universe. So that was a lot of fun. I'm going to continue to play around with these values. If you would like to download the code and try your own scenario, I'll leave it for you in the description below. Feel free to just play around with these values. Do be aware that this thing does need to run for about 24 hours to generate one of these graphs. So just be prepared to leave your computer running for that long. Anyway, thank you so much for watching. I'll see you next time. Bye bye.